This is Euclid Book 10, proposition number 60, and it goes something like this. The square on the binomial straight line applied to the rational straight line produces as breadth the first binomial. Let AB be a binomial straight line. So we have this AB right here, and it's a binomial straight line. And it's going to be divided into its terms at C. Okay? So that AC is the greater term. As you can see, AC is longer than CB. Let a rational straight line DE be set out. That's this one right here. And let DEFG, which is this whole thing right here, this whole rectangle, equal to the square on AB, which if we take this line here, we can actually make this line into a square where all four sides are going to be this length. Okay. Be applied to DE. Okay. Producing DG as its breadth. Okay, now what does that mean? Well, what it means is that we're going to apply this area to this line DE right here to make this whole thing right here. Okay? So, in other words, this whole area right here is going to be exactly the same amount of area as what's in this square. That is, if you drew everything out like you're supposed to. Alright, now, what is line DG? Line DG is across here, and that's the breadth of this. Okay. I say that DG is the first binomial straight line. For let there be applied to DE the rectangle DH. Okay, so where is the rectangle DH? It's going to be right here. This is your rectangle DH. It's DEHK. That's that one. And the area inside of here is going to be equal to the area inside of AC. Now, what is AC? Well, we took this line AC right here, and then we made a square out of it. And all four sides of this square are going to be the length of AC. And KL, okay, so now we have this KL right here, this rectangle KL. And the area inside of here is going to be equal to the area of the square BC. Now, where did we get the square BC? We took this line BC right here, and we turned it into a square. So all four sides of that square are going to be the length of BC. So the area inside of here is going to be the area inside of here. Therefore, the remainder, twice the rectangle ACCB, is equal to MF. So, what are we going to do on this? We're going to take the length of AC, and two sides of this rectangle are going to be the length of AC. We're going to take the length of BC here, and two sides of this rectangle are going to be the length of BC. And that's where we get that. Okay. Now this area here is equal to the area inside of all of this. All of this area right here. Okay. Let MG be bisected at N. Okay, so we're going to bisect this line MG, and it's going to be bisected at N. And let NO be drawn to let NO be drawn parallel to ML. This is now parallel to this. Therefore, each of the rectangles MO, this is one rectangle here, and NF, this is the other rectangle here, is equal to the the rectangle ACCB. Alright. So the area inside of here and the area inside of here is equal to the area inside of here. Okay. Now, since AB is a binomial divided into its terms at C, so this is a binomial, it's divided into its terms at C. Therefore, ACCB, this line here and this line here, are rational straight lines. They're commensurable in square only. This is by Euclid Book 10, proposition number 36. Therefore, the squares on AC and CB are rational and commensurable with one another. So this square and this square, these two squares right here, are rational and they're commensurable to one another. So if the sum of the squares on ACCB is also rational, this is by Euclid Book 10, proposition number 15. So if you added these areas together, it'd be rational. And it is equal to DL. Okay, now what is DL? DL is the area of this plus this. All of this is DL. Okay, so if we add these two areas together, we get this whole area right here. Therefore, DL is rational. This whole area is rational. And it is applied to the rational straight line DE. Okay. Therefore, DM is rational. Okay. So the straight line DM is also rational. And is commensurable in length with DE. This line is rational and commensurable with this. And that's by Euclid Book 10, proposition number 20. Again, since AC and CB are rational straight lines commensurable in square only, since this line and this line are rational straight lines, but they're only commensurable in square, therefore twice the rectangle ACCB, that would be this one right here, that is MF, that would be this area plus this area together, this whole area is this, it is medial, by Euclid Book 10, proposition number 21. And it is applied to the rational straight line ML. So we've applied this whole area to this line right here. Therefore, MG, this line right here, is also rational and incommensurable in length with ML. So this line and this line are not commensurable. Okay? Now, it also means that this line and this line are not commensurable. And this is by Euclid Book 10, proposition number 22. But MD, now what is MD? Okay. MD is this line right here. That's DM or MB, whatever you want to call it. It is rational and is commensurable with DE. Okay? DM and DE are commensurable and this line is rational. Therefore, DM, this whole line across here, is incommensurable with the length of MG. So DM and MG are not commensurable. This is by Euclid Book 10, proposition number 13. DM is rational, MG is rational. Okay. And these two lines right here, though they are rational, they are only commensurable in square. Therefore, DG is a binomial. This whole line here is a binomial. This is by Euclid Book 10, proposition number 36. It is next to be proved that it is also a first binomial straight line. Since the rectangle ACBC, this is that rectangle right there, is a mean proportional between the squares on AC and CB. Okay. So this rectangle is a mean proportional between this one and this one. And this is by the lemma after Euclid Book 10, proposition 53. Therefore, MO, well, what is MO? That's this rectangle right here. It's also a mean proportional between DH and KL. Okay. This rectangle is a mean proportional between this rectangle and this one. Therefore, as DH is to MO, as DH is to MO, so is MO to KL. MO to KL. So as this is to this, so as this is to that. Therefore, okay, that is, as DK is to MN. Okay, what is DK? That's this line right here. As DK is to MN, so is MN to KM. Okay? As this line is to this line, so is this line is to this line. This is by Euclid Book 6, proposition number 1. Therefore, the rectangle DK and KM Now where do we get this from? Two sides are this length, two sides are this length. That's where we got that rectangle from. Okay, so this rectangle area right here is equal to the square on MN. So if we were to take MN right here, we were to make a square out of it, that area would be the same as this. This is by Euclid Book 6, proposition number 17. So far, so good. And since the square on AC is commensurable with the square on CB, since these two squares are commensurable, DH is commensurable with KL. These two areas are commensurable. So that DK is also commensurable with KM. This line is commensurable with that. This is by Euclid Book 6, proposition number 1, and Euclid Book 10, proposition number 2. And since the squares on AC and CB, see these two squares right here, are greater than twice the rectangle ACCB, so if you add these two areas together, it's going to be bigger than that. If you add these two areas together, it's going to be bigger than twice the rectangle of this. So if you take this area, multiply it by 2, these two areas combined are going to be bigger than that. And that's by a lemma. Therefore, DL is also greater than MF. Okay. DL, which is this area plus this one, this whole thing across here, is greater than MF, which is this area plus this area. This whole area is greater than this whole area. So that DM is also greater than MG. This length right here is greater than this length right here. And the rectangle, DKKM, okay, that's this rectangle right here, is equal to the square on MN. Remember we made a square out of this line right here? That is to the fourth part of the square on MG. So we're going to take line MG and we're going to make a square out of it. Okay? And DK is commensurable with KM. Okay? And this line here and this line here are commensurable. But if there be two unequal straight lines, and to the greater there be applied a parallelogram equal to the fourth part of a square on the less and deficient by a square figure, and if it divided into commensurable parts, the square on the greater is greater than the square on the less by the square on a straight line commensurable with the greater, which is by Euclid Book 10, proposition number 17. Therefore, the square on DM, okay, if we were to make a square out of DM, we have that one, is greater than the square on MG. If we were to make a square out of MG, okay, so the square on DM is greater than the square on MG by the square on a straight line commensurable with DM. Okay? So there is some line that's commensurable with DM, which actually happens to be DE. So this square plus this square would be this square. Alright, and DM and NG, okay, and DM and MG, this line right here and this line right here, they're rational. And DM, which is the greater term, is commensurable in length with the rational straight line DE set out. Therefore, the whole length DG right here is the first binomial straight line. Alright. And that is the whole proof. I will tell you more in a future video. Stay tuned.